In this third lesson on exponential functions, you will learn a typical application of these functions to financial models. More precisely, you will study the growth of investments compounded once a year or several times a year. The skills required to master the content of this lesson are an understanding of the percent increase we covered in the second lesson in this unit. Let's begin by a fundamental distinction between simple interest and compound interest. In a simple interest models, you compute interest solely on the original amount invested. For example, suppose you start with $100 and suppose the interest is 8% simple interest annually, yearly. Okay, so simple interest yearly. How do you compute interest at the end of every year? Well, this is very simple. Here's a timeline. You start at t equals 0 with $100. Then, at the end of the first year, you're going to have to add 8% of $100. So this is $100. That's what you had at t equals 0. And then 8% of it, so that's just $8. Okay. But now, at the end of the second year, what happened? Well, what did you have at the end of the first year? You had $108 and you have to add the interest, but the interest is always computed on the original amount. So it's 8% of 100, which is again $8. I meant to write 2 right here, right? At the end of the third year, what do? Well, you take the amount that was at the end of the second year, which is $116, and you add the interest. But what interest? Again, just 8% of the original amount, which is just $8, right? And so at the end of the third year, you would have $124. And this is the simple interest model where the interest is only computed on the original amount. We will not be doing simple interest in this lesson. We're going to be looking at compound interest. In a compound interest model, the interest is added on the original amount invested and on all interest accumulated. So for example, again, I'm going to start with $100 and I'm going to take 8% interest compounded yearly. Okay, so this time it's not simple interest, it is interest that is compounded yearly. So what does it mean? Again, here's a timeline of the situation. We start at t equals 0 with the original investment. That was $100. Then what's going on at the end of the first year? Well, you have $100 that you invested and you add the interest, which is just, again, $8. And so you have $108. All right. So now what's going on at the end of the second year? Well, at the end of the second year, in your account, you have the $108 that was there at the end of the first year, and you have to compute interest. But the interest you compute, it's 8% of 108, not of the original, but on the amount that was there at the end of the first year. So it's the original investment and the interest added. You add 8% on these two amounts, okay? This is precisely $8.64. Now, what's going on at the end of the third year? Well, you would take the amount that you had in your account at the end of the second year, which is $116.64, and you have to add 8% of this amount, 8% of 116.64, and that is about $9.33. So you see, in the model of compounded interest, you take the interest on the principal every single time, but also interest on all the interest that you have accumulated. The formula for an investment compounded once a year is then very easy to derive. you keep on increasing the amount invested by the percent interest every single year. This is what we cover in the second lesson, right? And so every single year you multiply by 1 plus r, the original amount. So if you invest an initial amount of P naught dollars, after T years, you will have P naught times 1 plus r to the power of T. Sometimes P sub T, which describes the value in the account after T years, is denoted by FV, the future value. In this case, P naught is then called the present value, and that's just PV. Let's go over some application of yearly compounding. So here's the first example we'll do. You invest $5,500 at 4.25% compounded annually. How much do you have after 8 years? So we're going to apply the formula. In this case, the original amount is 5,500, and R, be careful, we want the decimal form of it, is 0.0425, which is 4.25%. All right. And so in 8 years, T equals 8 in this case, right? And so we have P sub 8 equals, so what is it? It is 5,500 times 1 plus 0.0425 to the power of 8. All right. So now let's take the calculator to compute it. So this is about $7,673.10. All right, next example. This time, $12,000 is deposited in a certificate of deposit account in order to provide for a child's education. How much will be in the account after 18 years if the CD pays 9% compounded annually? So what do we have here? P naught. P naught is also called the present value, is $12,000. Okay. R is 9%, so it's 0.09. And T equals how many years? 18 years. And so the formula is telling us that P of 18, the amount after 18 years, will be $12,000 times 1 plus 0.09 to the power of 18. Okay, let's take the calculator to compute it. So this is about $56,605.44. Here we go. All right, next example. The next example is a little bit different. In this case, we don't know the present value. We don't know how much we want to invest. What we know is that we want to have $100,000 in 18 years. So let me do a timeline of the situation. This is T equals 0, T equals 1, T equals 2, and then etc., etc., etc. And this is T equals 18, okay? And what I want is to have $100,000 in 18 years. Why do I do for that? I'm going to invest a certain amount. I don't know what it is. We call it the present value or P naught. And I'm investing it in a CD account that pays 9% interest compounded annually. So in this case, what do I know? I know P sub 18. P sub 18 is $100,000. I know T equals 18. I know R equals 9%, so 0.09. But I do not know P0. So what's the formula? The formula is P18 equals P0 times 1 plus R to the power of 18. All right. And then you solve this equation for P0, right? And so you have P0 equals, so you divide both sides by 1 plus R to the power of 18. That's all you do, right? So what do we have? We have P0 equals, so P18 is $100,000 divided by 1 plus 0.09 to the power of 18. And this is about $21,199.38. In this model, I always round up because I want to make sure I have $100,000 at the end of 18 years. If I round down, I probably will be a little bit short of $100,000. Let's now go over the second model that is used in finance. The second model is an interest rate R is a decimal form of it, compounded n times a year. So to understand the meaning of compounded several times a year, let's look at two examples. So suppose you're given a yearly interest rate of R is a decimal form of the percent, and you want to compound it twice a year. So R compounded twice a year. What does that mean? Let's draw a timeline to understand what it means. That means you're going to divide the year. This is the beginning, initial value. This is the end of the year. You're going to divide the year in two compounding periods. So this is half the year, right? 6 months, right? And at the end of the first 6 months, you're going to add R over 2 of interest, and then another R over 2 at the end of another 6 months. That's how you compute R interest rate compounded twice a year. Concretely, for example, if you take R equals 12%, which is 0.12, then what do? At the end of the first 6 months, right, half a year, 6 months, you're going to add 6%. And then at the end of the year, which is another 6 months, that's a second compounding period, you will add another 6%. This is how you compute 12% yearly compounded twice a year. All right, let's look at another model before we generalize. Suppose now the interest rate is R percent, let's say, but percent is not accurate, right? It's a decimal form of it. R yearly, but compounded 12 times a year, compounded monthly. That's 12 times a year, right? So how do you compute R interest rate yearly compounded monthly? So you take your year, and this time you don't divide it in 2, you divide it in 12, right? So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. All right. And what do you do at the end of the first month? You add R divided by 12 of interest rate. At the end of the second month, you again gonna add R over 12. So you divide the interest rate by the number of compounding period, okay? R over 12, R over 12. That at the end of every month. So at the end of the year, you've added 12 R over 12 of interest rate, right? So basically this is like R of interest rate, okay? Again, I'm sorry to say of interest rate. I want to say percent, but you know it's a decimal form of the percent. Again, for example, let's say 12% yearly compounded monthly, compounded monthly. So what do? At the end of every month, we're gonna add 1% interest rate, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And at the end of every month, I'm just gonna add 1% interest rate, okay? So if I do that 12 times, it's going to be 12 times 1%, and that will be equal, it's not really an equality, right, to 12%. That's how we compute an interest rate compounded several times a year. Let's generalize now. So this timeline describes a yearly interest rate of R compounded n times a year. What do? I take a year and I divide it in n compounding period, and at the end of each compounding period I add the interest rate of R divided by n, right? At the end of each compounding period, that's going to be my interest rate. How many compounding period in 1 year? N compounding period. And then the second year you're still going to have n compounding period. Therefore, over the first 2 years, how many times did you add R over n interest rate? 2n times. So that's a formula at the end of 2 years. And in general, at the end of the tth year, you're going to have n times t compounding period, and the interest you've added at every compounding period is R over n. That's a formula that describes an interest rate of R yearly compounded n times a year. Let's go over some examples. Okay, in this first example, you want to invest $5,000 in an account that gives you a return rate of 7.25% yearly. You wonder how much will be in your account after 5 years, but you are given different schemes of compounding. The first question is, how much do you have if you compound every 2 months? So compounding period is 2 months. How many compounding period do you have in a year? 6, right? 6 times 2 months equals a year. Okay. So my initial investment is P naught is $5,000. R is 0.0725 and T is 5. In the first case, N is 6, so P sub 5 on the fifth year, I will have, this is a future value, I will have 5,000 times 1 plus 0.0725 divided by 6 every 2 months. This is the interest rate you're going to add to the power of 6 times 5. All right, there are 30 compounding period in 1 year. Okay, so what is this amount? Let's take the calculator. So you will have in your account $7,168.99. Okay. In the second compounding schemes, you are compounding every 4 months. Now, how many 4 months in a year? Well, you got 3 4 months, right? So n equals 3. There are 3 compounding periods in a year, right? So the same formula becomes P of 5 is 5,000 times 1 plus 7.25%, but now I have to divide it by 3. There are 3 compounding periods in a year, and in 5 years, there will be 15 compounding periods. All right, calculator. So this is about $7,153.68. By the way, please notice the first amount is larger, which makes sense because we had more compounding period than in the second cases, okay? What about the third case? I'm compounding every day. So, how many days in a year? Well, let's just take a regular year with 365 days. So in this case, the formula becomes 5,000 times 1 plus 7.25%, so divided by 365 days in a year, so 365 compounding periods in a year times 5 because we want it after 5 years. I'm expecting something higher than 7,168. And the amount this time is $7,184.32. Indeed, when you compound every day, it is going to be higher than when you compound every 2 months. Okay? All right. Let's move on to the next example. In the next example, I want to invest $12,000 in a CD account. The CD pays 9% yearly, compounded monthly, and I want to figure out how much I have after 18 years. So what is P naught? P0 is the amount I'm investing right now. That's a present value, $12,000. What is R? R is 9%, so it is 0.09, but I have to compound it monthly. So I'm going to have to divide 0.09 by how many months in a year? 12. There are 12 compounding periods. This is the interest I'm going to add at the end of every month, and I want to do it for 18 years. Okay, so how much do we have after 18 years? Well, I will have the initial investment times 1 plus 0.09 divided by 12. And then how many compounding period in 18 years? Well, 12 a year and then 18 years. So this will give me the amount at the end of 18 years. Let's take the calculator. And so there will be about $60,271.65 at the end of 18 years. Next example. In this example, I want to save for a child's education. My goal is to have $100,000 in 18 years. The account I invest in is a CD that pays 9% yearly, but compounded monthly. Okay, so this is a present value problem, what we call a present value problem. I'm wondering what's the initial investment. Okay, so what do I know? I know P18. P18 is $100,000. This is what I want to have in the future. Okay, T, how many years? Well, 18 years. My rate R is 9%, right? So it's 0.09, but I compound monthly. So the interest rate I'm adding at the end of every month is 0.09 divided by 12. Okay, and so the equation I have to solve is P18 is $100,000. This is what I will have when I invest what I'm looking for. Again, here the problem is what are you investing? So P naught I'm looking for times 1 plus 0.09 divided by 12 to the power of 12 times 18. So again, you divide both sides of this equation by 1 plus 0.09 divided by 12 to the power of 12 times 18, and you will find what P naught is. Okay, so to do that, of course, we're going to use the calculator. Let's see what it is. And so I found $19,909.86. Again, I always like to round up to make sure I have the amount I won, which is $100,000 after 18 years. Let's go over one more time on the concept of compounded interest, which is interest on interest. What does it mean? To explain it, I have looked at three models. Of course, they are highly unrealistic. I'm looking at 100% interest yearly. That's simply doubling, right? Why did I take this model? Because I wanted to play with shapes, and doubling is easy. I just take the shape of the same size. So in this model right here, you have your initial investment and then you double it at the end of the year. This is 100% compounded yearly. Okay, there is no interest on interest. The interest you add at the end of the first year is entirely added on the investment, on the principal. That's the principal. Okay, let's look at what happens when you compound 100% yearly twice a year. So this time, at the end of 6 months, you're going to add 50% interest. So this shape is half the size of this one, right? Because it's just 50%. Okay. And then let's go another 6 months. So what do we have? We had the original investment, right? This is still going to generate another 50% interest. But now this interest here on its own has generated a 50% interest. The size right here of that shape is half the size of the rectangle right here, okay? This is the interest on interest and not on the original investment, right? This is the interest on interest, right? So at the end, if you compare the two models, you did have, this is like 100%, right? So this is the same size as this. This is what we had in the previous model, that right here. But when you compound twice a year, you add interest on interest right here, this square. And so the third model I'm going to be looking at is when I compounded 4 times a year. So this time I take 100%, compounded 4 times a year. So you divide it by 4 and that's 25%. So I want to look at what happens when I add 25% at the end of every 3 months. All right, now you can see right here at the end of 3 months, the principals generate a 25% interest. This shape is 1/4 of the size of the original interest right here. At the end of the second 3-month period, then the principal is still going to generate another 25% interest, right? But this interest right here on its own generate a 25% interest right here, a shape that is 1/4 of the size of that square. And then let's look at the third one. So what happened when you add 9 months? The principal is going to generate 25% interest. This interest that you added right here is going to generate 25% interest. This is going to generate a second 25% interest. You already generated the first one right here, right? It's going to generate the second one. But now this interest right here will also generate a 25% interest. And if I add one more period, I am not going to describe all these red shapes right here, these red square, but every red square is interest on interest. You can see right here, you have the 100%, right? The doubling, and then everything right here is interest on interest. So it is more than compounded twice a year, and it's surely more than compounded once a year. Okay, so I will stop this video here. I hope everything was clear. Thank you for watching.